How would you image an atom? We use optical microscopes to look at cells, so why not just take that and make it stronger? Well, light has a fundamental diffraction limit, which means that we can't just keep scaling up our optics to see smaller and smaller things. If we want to see atoms, we'll have to do something clever. This is where the Scanning Tunneling Microscope, or STM, comes in. STM works by taking a sharp metal tip incredibly close to a surface. This generates a measurable current. Then, we raster scan across the surface and measure the change in current. This simple but powerful technique allows us to see the atoms on a surface without having to worry about wavelengths or optics. Now, in this video, I'll be covering the details on how STM works. But STM inspired a whole field of imaging called scanning probe microscopy, or SPM. And many of the techniques I'm describing will also apply to other methods like AFM or ENSOM. So, if a technique is used in another SPM method, I'll note it in the corner. If it's just for STM, I'll note that instead. STM works because of tunneling. Quantum tunneling deserves a whole video of its own. But for our purposes, you only need to know two things. Number one, no touching. Quantum tunneling allows us to generate a current without the tip ever making contact with the sample. Number two, exponential decay. The amount of current is exponentially proportional to the distance between the tip and the sample. So, we bring the tip close enough to the sample for tunneling to occur. Then, we raster scan the tip across the surface. The tunneling current's exponential decay makes the system sensitive enough to detect the difference between being directly over an atom and in between atoms. As we move the tip across the sample, we use a feedback system to stay in tunneling. We can either keep the height constant and measure how the current changes as we move, or we can keep the current constant and measure how we have to change the height to keep the current steady. Both moving the tip across the sample and bringing the tip close enough to get a steady signal without crashing requires nanometer precision in positioning. This can be done by piezoelectric crystals. Piezos are neat. By applying a voltage, you can change the actual size of the crystal. The change is typically on the order of a few hundred picometers per volt, and this is small. But that means that we can move incredibly small distances by applying very small voltage changes, and moderately small distances with even higher voltages. Piezos in different clever configurations are used to achieve the displacements required in both STM approach and in scanning. So far, I've been avoiding the linchpin on which this whole system hinges, the tip. When I said a sharp tip in the beginning of the video, I meant sharp. A tip that is large enough to tunnel across several atoms will get an averaged out signal between the atoms, which will destroy any hope for atomic resolution. So, we need a tip that tunnels to one atom on the surface, which means the tip must be atomically sharp itself. This seems like it'd be a feat of engineering to accomplish, but recall what I said about tunneling earlier? The tunneling current exponentially decays with distance. This means that if you get a sharp enough tip, it's very unlikely that two atoms on that tip are at exactly the same distance from the sample. So we essentially get a signal from one and only one. Now, I've been simplifying a bit. Atoms are not hard little balls, but are better thought of as clouds of electrons. Depending on the element, these clouds can have different shapes. the most common being S, P, D, and F. The shapes of these clouds will change the shape of the tip. So, just as a blunt tip, which images several atoms, can't give us atomic resolution, you can imagine that a surface of atoms having spiky D or F orbitals being imaged by a tip with a nice smooth S orbital at the end will end up looking a lot more like the rounded tip shape than the jagged surface. So it's not just topography that we see, but also the electronic structure of the atoms is going to change what we image. This convolution of topography and electronic structure means that we have to be careful in interpreting our images. But this also means that we can use STM to do spectroscopy. By wiggling our tip height, we can extract information about the work function of the material, while wiggling the bias voltage gives us an idea about the local density of states. The combination of these two powerful techniques, real space imaging of the atoms on a material, and the ability to perform spectroscopy at the atomic scale, have made STM an invaluable tool for condensed matter physics. As I mentioned, the method has spun off a whole field called scanning probe microscopy. From variations of the STM, like spin-polarized STM, to the easier-to-use but lower resolution AFM, its own spin-offs, and a variety of other techniques. The invention of STM was the starting block of locally resolved surface science, and very justifiably won the Nobel Prize in Physics in 1986. On a personal note, I love the fact that I can say that my research lets me look at atoms.